In acid-base 1, we covered what's the next best step. That is, how you figure out what the acid-base derangement is and then maybe what the cause might be. In acid-base 2, we're going to talk about how to actually interpret a blood gas. You're going to get this on the test in the way of what is the acid-base disturbance, and you'll have a list, respiratory and metabolic, gap and non-gap choices, and you have to figure out which one is present. The way you're going to do this in life is by actually grabbing hold of that ABG printout and working it through. The same steps can be followed regardless of what the original derangement is. And then once you get to step 3, they start to change a little bit. Step 1 is to look at the pH. Step 2 is to look at the CO2. That's how you determine what the primary disturbance is. And step 3 is going to be, is there another problem? Let's start off with respiratory first. Remember, step 1 is to look at the pH, acid or base, alkalemia, acidemia. The second step is to look at the CO2. And here's how I want you to look at this. If you've diagnosed an acidemia, ask yourself, if it were respiratory, what would the CO2 be, high or low? If it's acidemia and it's from respiratory, you expect the respiratory acid to be high. That is, if the CO2 is high and you have an acidemia, your primary disturbance is respiratory acidosis. If your pH is acidemic and your CO2 is low, it's a metabolic problem. On the flip side, if the pH is elevated and you expect it to be from the respiratory system, you should see a decreased CO2. In that case, you'd know you'd have a respiratory alkalosis. If your pH were high and your CO2 were also high, and then the acid-base derangement that's primary would be metabolic. We're sticking with respiratory to start. Step 3 is there another acid-base disturbance? 3A is to check the anion gap. Doesn't matter what the primary disturbance is, always check an anion gap, because if the anion gap is elevated, you know that you at least also have an anion gap metabolic acidosis. But for respiratory disturbances, which is why we're doing them together, both respiratory acidosis and alkalosis, step 3B, and is there another, is to determine acute or chronic. That is this current problem acute or chronic? We'll talk about how to do that in a minute. And then you say, is the CO2, that is the bicarb, is the bicarb appropriate? How do you determine chronicity? I want you to start thinking about dime changes. Right? For every 10 change in CO2, for a dime change of CO2, for every 10 points the CO2 changes, other stuff happens. So for every dime of CO2, the pH will change by 0.08 if it's acute and 0.04 if it's chronic. In respiratory acidosis and respiratory alkalosis, same thing. Dime change of CO2, the pH will change by 0.08 if it's acute and 0.04 if it's chronic. So what you do is say, what is my pH right now? What is my CO2? Calculate the change in pH from normal, 7.4. Whichever your current pH is at, or closest to, you pick acute or chronic. And you have to do this to see if the bicarb is appropriate. Because for every dime change of CO2 in respiratory acidosis, the bicarb changes by 1 in acute and 3 in chronic. And this is where it changes. Respiratory acidosis, bicarb 1 and 3. Respiratory alkalosis 2 and 4. For every dime change of CO2, the bicarb changes 2 in acute, 4 in chronic. And the bicarb should change in the direction to bring the pH back to normal. So what you do is you look at the CO2. It's a respiratory problem. Whether it's acidosis or alkalosis, you calculate the change in the pH based on how many dime changes of CO2 you've had. Then you say, I know what my bicarb change should be, and ask yourself, is the expected bicarb equal to the bicarb given? If you have too much bicarb, regardless of which it is, if you have too much bicarb, that is the given bicarb is greater than expected, you have too much base, and therefore you have a coexisting metabolic alkalosis. If you have too few bicarbs, that is the given bicarb is less than expected, and you have too little base, and you have an additional metabolic acidosis. That's respiratory. Let's tackle metabolic next. In metabolic acidosis, you're going to follow the same first two steps. Then step 3 is going to change a little bit. Because it's a metabolic acidosis, the pH is going to be low. If you suspected it to be from the respiratory system, you'd expect there to be too much respiratory acid. And so you would expect the CO2 to be elevated. But because it's metabolic, in fact, you'd see the CO2 be low. Low pH, low CO2 means not respiratory acidosis, so therefore it is a metabolic acidosis. Third step, are there other problems? 3A, same thing as before, calculate the anion gap. The anion gap can be calculated by the sodium minus the chloride minus the bicarb, given to you on the BMP. You compare that to a normal anion gap, which is 12. If what you calculate is greater than normal, you have an anion gap. 12 is going to be used as the normal on the test. In life, 12 is an approximation of normal based on the albumin. What you should take away is that an albumin times 3 is a normal anion gap. Now, regardless of whether you have an anion gap or not, you're going to decide, is the PCO2 appropriate? You do that with Winter's formula. Winter's formula is 1.5 times the bicarb plus 8 plus minus 2. A little fudge factor, a little wiggle room you've got. So what you do here is you take the bicarb you're given, you plug it into Winter's formula, 1.5 times that bicarb, you add 8 to that, and you've got arranged, this is plus minus 2. If your CO2 that you are given is greater than expected, that is, the expected being calculated by Winters, the thing you're given on the paper is greater than what you calculated, you have too many respiratory acids. Therefore, you have a respiratory acidosis. If what you're given is less, that is below the bottom of the range you're expected, you have too few respiratory acids, that's a respiratory alkalosis. And so in addition to your metabolic acidosis, you'd also have a respiratory problem. Now, let's be very clear on this. Only time that you say respiratory acidosis or respiratory alkalosis in addition is if your CO2 is outside of Winter's formula. The CO2 may not be normal. It may not be 40, but if it is appropriate for Winter's formula, it is not another acid-base disturbance. The final piece of this is there another bicarb problem? You only do this if you had an anion gap acidosis. One way to do this is to use the delta-delta, and I don't use it. I don't remember how to calculate it, and I don't remember what corresponds to what. So I don't use the delta-delta. I use the add back method. Far simpler. Let me show you how it works, and then we'll talk about it. In this example, you've got a BMP. The sodium is 140, chloride is 100, bicarb is 10. The anion gap is 30, 140 minus 100 minus 10. We know that a normal anion gap is 12. And so to get from 12 to 30, we had to add in 18 hydrogen ions. Those 18 hydrogen ions correspond to 18 bicarbonates. So to get the starting bicarb level before the anion gap, you have to add these 18 bicarbs to the bicarb we're given. It seems weird. Why would you do that? Just play along and you'll see where this goes. You take the combination of the bicarb and the amount of acid it took to get to the current anion gap, add it back to that bicarb. In this example, what we get is 28. Normal is 24. If you have too many bicarbs from 24, you have an alkalosis. If you have too few bicarbs from 24, you have an acidosis. So in this example, even though we have a very large anion gap, we started off with a metabolic alkalosis. So this would be represented as anion gap acidosis with metabolic alkalosis. Let me explain it a little bit again. The key to this is figuring out how many acids you need to get from your normal gap to your current gap. Add that number back to bicarb. That's going to be your calculated. If your calculated bicarb is greater than normal, that is 24, you have too many bicarbs. This is a metabolic alkalosis. If your calculated bicarb is less than normal and is less than 24, you have too few bicarbs, and this is a metabolic acidosis. In this case, you would say you have an anion gap acidosis with a non-gap acidosis. That's a hard one. We're going to end on a much easier one. Alkalosis, the pH will be up. If it were from the CO2, in order to get an alkalosis, you expect the CO2 to be low. But in this case, it'll be high, meaning that it's a metabolic alkalosis. You can stop there. Metabolic alkalosis means the aldosterone is up. There's no equations you have to remember, and you won't have to adjust for the CO2. You won't have to determine if there's another disturbance. If metabolic alkalosis comes up, it will either be on its own or it will be part of another disturbance, either respiratory acidosis with metabolic alkalosis or an anion gap metabolic acidosis with metabolic alkalosis. So if you found the primary disturbance to be metabolic alkalosis, the only thing you need to do is check that anion gap to make sure it's not elevated and you're missing that anion gap metabolic acidosis. To conclude this is really hard, and most people don't get it. And for a lot of people, they spend a lot of time trying to get it, and then there's only one question about it, and they spend 15 minutes on it, and they still get it wrong. So after watching this video and trying out some of the problems and the questions, if you don't get it, when it comes to test day, just take the hit. Pick C or the one with the most disturbances and move on. As a study point or strategy on the test, don't waste time on a question you're not going to get. So if you master this, you're going to get it right. But if some reason on test day you're struggling with the question, pick something, move on, and if you have time at the end, go back and try to figure it out. That is acid-base gas interpretation.